Comparing operational amplifier gains for 4 cases presented here based on the situation of the two switches is insightful. And to do that, let's just consider case 1. This is a circuit realized with 1 op amp. So case 1, where we have this situation that we are saying S1, let's assume S1 is shorted, so S1 is closed, and let's say S2 is closed as well. So both of them closed. As a result, you have S1 closed, S2 closed, R short, Vx short, effectively positive input terminal connected to ground shorted. So in this setup, you have just this simple scheme. You have Vn, and you have just resistor R and resistor R, and here you get connected to ground, and then you have the op amp in negative feedback, assuming linearly biased and not in saturation, ideal op amp. This is the setup. So this is a classical inverting amplifier. You have positive terminal connected to ground. You have negative terminal here. Virtual short is valid because op amp is a linear mode of operation. Positive terminal 0, therefore negative terminal 0. And you can simply write that Vout is equal to negative feedback resistance, which is negative R, divided by input resistance, that is R, times Vn, which means, as expected, Vout is equal to negative Vin in this setup. Gain from Vin to Vout is basically negative 1, as expected. I mean, aside from knowing that this is obvious, you can just simply write a KCL at this point. Whatever current that goes into this resistor R, whatever current that goes into that resistor R, I can change the color, should be the same current that goes through this resistor R, because nothing can go through input terminal of ideal op amp with infinite input impedance. So you can write a simple KCL there. You can say Vin minus 0 volt at negative input terminal divided by R is equal to 0 volt minus Vout divided by R. And this obviously gives you the same thing as you can see here. Okay, so we are done with case 1. Let's move on to case number 2. So I am going to move on to case 2 where we assume that, so case 2. In this case, I'm going to make the assumption that, let's make the assumption that R is there, but Vx disappears. So I'm going to assume that S1 is open, so R is not shorted, but S2 is closed. Since S2 is closed, Vx is shorted to ground, so the only thing connects the positive input terminal to ground is just resistor R. So your setup looks like this. So you have Vn coming in and goes to 2 resistors as you have. And then from here, at the positive input terminal with a resistor, you go to ground. And you have your op amp, again linearly biased, not saturated, ideal op amp. So virtual short is valid, meaning that the positive input terminal and negative input terminal, they should have the same voltage, and then Vout. Okay, so same simple scenario. You have Vn, and it's contributing to Vout via in two ways. One via the inverting amplification, the other one is via non-inverting amplification through positive terminal. But one thing you can quickly say, I can quickly use the formulas. If you want that, then it would be like this. Vout equal to, just show you the quick computation way. So you would say the negative or inverting amplification contribution like the above. So you would say negative R, feedback resistance R divided by input resistance R times Vn. That's one way. And the other way is Vn going here. So from this point, you have an amplification that is 1 plus, I'm going to prove this, feedback resistance R divided by input resistance R times the voltage at positive input terminal, which is half of Vin. So Vin over 2, and you can see this whole thing becomes 0. So my anticipation is, as I showed here, Vout will be shown that in this setup, in this case number 2, to be 0, and nothing comes out actually. So the gain is 0 in this in this case number 2. But I can show you now this way if you want to see a proof of this rather than using the formulas we know from the standard inverting and non-inverting amplifier. So you have V incoming, and nothing goes through the positive input terminal of op amp because input impedance of ideal op amp is infinite, so the current here is 0. Now, there is a simple voltage division between RR, so no wonder that V positive, which should be equal to V negative because of mutual short, is equal to voltage at positive is V in over 2 because it's a voltage division between RR, so V in over 2. Now, the voltage here is V in over 2 as well. I can just write a simple KCL because whatever current goes in, that current should also go through the feedback resistor because again, no current goes through the input terminal of op amp, ideal op amp with infinite impedance. So V in minus 0 divided by R is equal to, sorry, not 0, V in minus V minus V in divided by 2 R equal to V in divided by 2, voltage at the negative terminal, minus V out divided by, so V in divided by 2, minus V out divided by R is this current, which should be equal to that current. That's the meaning of this KCL I'm writing. Okay, this is obviously equal to resulting V out equal to 0, as expected. So um, we are done with case number 2. Now let's do case number 3, which I'm gonna just clean up here. So this is my case number 2 finished. Okay, for case number 3, what am I assuming? So case 3, let's assume in this case that now S, we can make a lot of assumption, but let's make assumption that the S1 open, S2 open as well. So S1 open and S2 open as well. So both of them open. Therefore, the circuit is exactly as shown here as if switches are not there, because everything would be in place. Vx is in place, R is in place, we have connection to plus. Okay, so if that is the case, we have two input voltages, one Vx, the other one Vn, contributing both to V out. We have to use superposition in this linear setup, assuming op amp is in linear region. To do the superposition, we once consider Vx is not there, shorted, and we see what Vin is doing to V out. We keep it, and then next time we assume V in is not there, which means V in is 0 or shorted, and then we consider Vx. Okay, if we assume Vx is 0, not there, we get to exactly what we see in case 2. So um, in case 3, when when Vx as a part of superposition, when Vx is 0, we can see that situation becomes like case 2 for Vn. Um, and then as a result of that, so I'm saying um, situation for Vn is like case 2. Therefore, V out equal to 0. So V in is not doing anything at V out, even in case 3. Now, the only thing that can do anything at the output is just the presence of Vx. So in that setup, I have this situation. So I have my op amp and negative feedback, and I have resistor R. I make the assumption that V in is 0. So V in is 0 because I know V in is not doing anything. And all I can see is I have R and I have my Vx. That's it. And then what I see is resistor R, and I can see the V out. That's my circuit now. And of course, we can compute it again using two different methods. One is brute force technique. So in the brute force method, I can just say, okay, V out is just in this setup. I'm just dealing with purely non-inverting amplification because my contributing voltage is connected at positive terminal, resulting in, if you look at this circuit, Vx, current flows through R, and that same current has to go through this resistor because nothing can go through the positive input terminal of ideal op amp because it has infinite impedance. So that same current has to go, that same current, let me change the color, that same current has to go this way from Vx toward the ground. So that means there is a simple voltage division between R in series, and voltage at positive terminal in this op amp, in this setup, will be just equal to Vx over 2. And of course, assuming the circuit is a linear operation, virtual short is valid, V positive should be equal to V negative as well. If I go brute force here, I can say it's a non-inverting setup amplification with a single op amp, so the V out versus as related to V in is simply 1 plus feedback resistor, which is R, divided by input resistor, which is R, times the voltage at the positive terminal, which is of course Vx over 2. And you can see that 1 plus R over R is 2, and 2 cancel out each other, and therefore V out becomes equal to Vx. That is the conclusion in terms of what we have for output voltage as a function of input voltages. Vx is only contributing here. You can also write KCL if you want to prove this, but it is the same as what we did before. So voltage drop across R on top should be the same as voltage drop across R at the bottom because they are effectively in parallel because they have the same voltages on the two terminals of each other. So if Vx over 2 drops across this voltage, Vx over 2 drops should across this voltage. And then because the current going through this resistor is the same current that is going through this resistor, the voltage drop across this one is also Vx over 2. And there you go. Since the voltage at negative terminal is equal to positive Vx over 2, you're adding a Vx over 2 on top of it, therefore V out becomes Vx, as expected. Okay, so that is almost wrapping up because the only thing that is remaining is case number 4. And in case number 4, what we are assuming is the only remaining situation for the switches, which means I am assuming now I'm assuming that S1 is closed and S2 is open. So S1 is closed and S2 is open. In that case, I end up with the only remaining situation, which is V in is there, resistor R is there, this resistor R is there, S1 is closed, so R is shorted, is not there, Vx is directly connected to positive input terminal of op amp, and negative feedback is there, so feedback resistor R is there, and we go to V out. Okay, what is the situation now? Well, again, superposition, so use same as what we did in case 3, use superposition. Once find the contribution of V into the output, once find the contribution of V output, Vx to the output. So if we assume Vx is not there, so Vx is 0, so therefore shorted, positive terminal then is connected to ground, that exactly go back to case 1 in terms of what we have for Vn. So if Vx is 0, we are back to case 1. And as a result, it means V out is simply negative V. That is contribution of V into V out. Now, if, let me put it this way, if now V in is 0, if V in is 0, let me just Okay, if Vn is 0, then the circuit becomes as simple as the fact that again you are shorting here because Vn is 0, so your circuit is now simply connecting Vn to 0 and Vx is that positive terminal alive. That means you have a non-inverting amplification, Vx at positive terminal, and you can just simply solve it. If you want to go brute force, you can say it's a non-inverting amplifier, so non-inverting inverting op-amp scenario, op-amp case, and as a result, we know for that scenario that V out is, maybe I just write it here. Maybe I just write it here. So in that case, V out is equal to just 1 plus feedback resistor R divided by input resistor R times voltage at the positive terminal, which is Vx. Therefore, you end up with 2 times Vx. Okay, we considered superposition case 1 and case 2. The result is the sum of the both of them. So A uh, plus B, A, let me put it this way. Therefore, in summary, 1 plus A plus B, resulting in V out equal to negative V in plus 2 times Vx. That is the final outcome in case number 4, concluding the comparison of the output and corresponding gains for the 4 cases.